Hello all. Today we'll continue our discussion on instruction set architectures and develop more on the operand models, addressing modes, and elements of ISAs. We'll also talk briefly about interrupts at the end of the class. So let us review some of the well-known operand models, which determines many things in the corresponding ISAs and microarchitecture, such as average code size, memory access frequency, the programmability, etc. The first model is the three-address mode, in which case the three memory locations A, B, C take part in an arithmetic operation add simply makes three memory accesses and get the values at locations B and C and get them added and then store the result in memory location B. Another model is based on a single data register called accumulator. This model is also known as single address mode, and as you can see, instructions accept a single address to execute an operation. Having an extra register decreases the number of memory accesses we make. Yet another model called stack model, it does not use any address for arithmetic operations, but there should be an address for example, loading and storing. In the stack programming context, push and pop are the loading and storing instructions. The data is stored in a stack, which is usually a specific part of the memory or a set of registers in different modern CPUs. And the stored values are used to compute results. For example, after pushing some values into the stack, the add instruction gets the first two values in the stack and compute the addition, and then writes the result at the top of the stack as shown. This operation is achievable and it's performed with the help of stack pointer, which is automatically incremented and decremented. We could use more registers as shown to the right of this slide. The number of addressed registers or memory locations could be 2, for example. And in this two address mode, memory and registers are used together to perform operations. Registers can be used to perform operations to reduce the number of times the memory is read and written. In that case, all arithmetic operations are done between registers, and this model is referred as the load-store architecture. We could replace R1 and R2 in those assembly list of instructions shown. For instance, with memory locations, in that case, we will increase the memory access frequencies, but yet decrease the number of registers that we need in the microarchitecture. So this model is known as memory-memory model. As you might have already realized that choosing between 0 address, 1 address, 2 or 3 address operand models, we can classify ISAs. And there are a lot of trade-offs between them. Choosing one of the models, for example, also have an effect on the instruction code size. Having more registers, for example, call for more bits in the ISA to address those registers. So as we go from memory-only model to load-store model, the average code size should increase. On the other hand, memory-only model, while executing these operations, can access memory every time an instruction is fetched and executed. Some of them might be unnecessary, but mandatory because there need to be some temporary storages for calculating, and storing the final result. In that case, load-store model would outperform the memory-memory model as far as the data memory traffic is concerned. The memory accesses are usually very slow compared to the register accesses, and this is due to manufacturing process, physical properties of the storage technologies, etc. Therefore, the trend with the modern architectures is that people start to move towards stored and load models. As you can see, x86 has 8 registers and MIPS has 32, and then the 30-bit Intel's architecture has 128 registers. In general, ISAs consist of many fields, such as opcode field, which tells us which operation to be executed. The address field makes us differentiate whether we use a memory address or register address, and which of the registers, for example, as well. The address field can be interpreted differently based on the mode of operation. For example, address could be the operand's address in memory, or it could be the address of the register, which holds the memory address of the operand. As you can see, we interpret the address field, the way that we interpret the address field could be encoded, and this is encoded in the mode field usually. And there might be other fields also, depending on how complex is the ISA, and as the number of, for example, the number of shifts we're supposed to perform could be part of the ISA. As we mentioned before, the addressing modes are abundant. In RISC approach, for example, in the reduced instruction set computer approach, only few of these modes are used, whereas the complex architectures, for example, use many more than listed in this slide. Let us review the most common addressing modes here, just to give it an idea, what kind of addressing modes we can have in an ISA. In the register mode, we use the value in the register as the operand, directly. And in the immediate mode, you use the value in the instruction as the operand. There's an absolute and direct mode, and that uses the immediate as the address. And the register indirect use the value in the register as the address, and memory indirect, on the other hand, uses the register value to address the memory location which holds the address. There is also PC relative mode, which means that the PC value gets added with an offset, which usually is specified by the immediate field of the ISA, and the sum of the two determines the address. There's also displaced and indexed. They're kind of similar to each other. The displaced uses the register value plus the offset as the address. Index mode, as I said, is very, very similar to displaced, and it could either add two index registers to compute the address or add the value of the index register to the address field of the instruction. There are also auto increment, auto decrement mode, which uses the register value as the address of the operand, and right after that, the register value is incremented automatically, so without needing an extra instruction to perform that operation. This might be useful, for example, when as a high-level programmer, when we define and use arrays, or we do arithmetic with arrays. You can add many more modes to this list, but the question you need to think about is, why do we really need so many addressing modes? Well, perhaps we don't, but we may if we want to make the high-level programmer job easier, and it's also if you want to provide more flexibility, right? So I want you to think about it. So let's consider an example to fully understand the addressing modes. Consider the memory shown to the right of this slide. The memory locations are shown in bold, and the locations 100 and 101 hold the instruction that is stored as 2 words. So the program counter is set to 100, so we can start fetching the instruction from the correct position in the memory. There's an index register called R, which holds the value 123, and there's also an accumulator register. Okay, and so let us say the opcode of the instruction is assumed to be loading the operand into the ACC. Okay, and depending on the addressing mode, different values can be loaded into ACC. The ACC is, by the way, is the accumulator register. So it's left as an exercise to fill the ACC depending on the different addressing modes. But let me show you what ACC will get if the mode is absolute and direct. Okay, in that case, the address, in other words, the immediate field of the ISA, will tell us the memory location to read the operand value. And we have 234 in that location, so as a result, ACC will be 234. As a small note here, since our PC, the program counter, must increment as we read the instruction, the moment we finish reading the address field, the PCC is now pointing to the 102 because it's incremented. So consider this while you answer the rest of the questions. We have already mentioned about complex versus simple instructions, yet again here we highlight the advantages and disadvantages. For example, one of the advantages of complex instructions is increased code density, better memory utilization, less off-chip bandwidth requirement, and better cache rate. Also, it enables simpler compiler design. A disadvantage is less opportunity for compiler optimization and more complex hardware. For example, FFT computation, string copy operation, or an evaluation of a polynomial, they're all examples to complex instructions. On the other hand, XOR, AND, NAND, or other logic operations like NAND or NOT operation or AND operation, these operations are examples to simple instructions. So this brings us to an important trade-off world, as illustrated by the picture shown. If we have two levels of semantics drawn by blue lines, one for high-level language and the other for control signals for the microarchitecture, then the question is, where do we place the ISA? If we have placed the ISA close to high-level language, then our instructions are going to be probably more complex. However, this would close the semantic gap between the instructions and the high-level language, so that the instruction will will like, they will be like functions in that case, the closer, and it's easy to understand. On the other hand, if you place the ISA close to microarchitecture, lower level, then perhaps our complexity of instructions will decrease, yet the semantic gap will increase. And an increased semantic gap will lead to more and more instructions to be generated by the compiler and the optimizations of these instructions, as well as the order of execution as well. So apparently, increased semantic gap can increase the complexity of compiler design. So such a design choice had led to two well-known movements in the history: reduced instruction set computer RISC and also the complex instruction set computer CISC. So we'll discuss more about these approaches later in the class. There are also issues like fixed length code size, a variable length code size, and fixed length, instructions, like easier to decode the decoder logic, wastes bits in instructions most of the time, because when the instruction is simple, harder to extend because you have only limited number of possibilities with the opcodes and all that. And the variable length instructions, on the other hand, they're more complex to decode. Complex encoding saves space and bandwidth, by the way, and ISA is extendable. And another issue is the uniformity of the ISA, in other words, where the opcode mode and address fields are located. Uniform instructions are easier to manage and decode, and yet can waste space and are non-compact. Great examples to uniform ISAs are like MIPS and Alpha, which we have seen in the previous classes. And a great example to the complex and non-uniform ISA is the x86 ISA, for example. There are three major types of instructions: data transfer, data manipulation, and control instructions. Load and store operations are for example, data transfer operations. Data manipulation instructions could be either arithmetic, logical, and shift operations, and you can see the examples are written in this slide. There are also control instructions. Control instructions are used to alter the control flow of the program by changing the values stored in the program counter. Program control instruction causes a break in the sequence of execution of instructions. For example, branch and jump are the most common of all the control instructions, but there are also other, like calling a procedure, returning from a procedure, compare and test. Branch and jump instructions can be either conditional or unconditional. A conditional instruction checks a condition before altering the corresponding program counter value. Sometimes program status register is used, and it contains condition codes. It's just nothing but a sequence of status bits. A conditional branch instruction can test one or more of these status bits for a condition. If met, then the control is going to be transferred to an effective address. Branching or jumping can also be based on relative magnitudes of two unsigned and signed numbers. For instance, greater or less than, or and equality conditions can all be used to take branching or jumping decisions in the program control flow. I also want to touch upon the interrupts before closing this session. A program interrupt is used to handle a variety of situations that requires a deviation from the normal flow of the program sequence. A program interrupt is similar to a function or a procedural call, so that the control is transferred to another service as a result of an externally or internally generated request. Likewise, the control returns to the original program after the service is executed. Apart from procedure calls, or simply calls, interrupts causes unpredictable changes to control flow. The interrupt service address is determined by the hardware, for example, rather than the address field of the instruction. In the procedure call, usually the address field of the instruction determines that. And finally, in addition to the program counter value, the contents of the register set are also stored somewhere, so that when the control returns to the program, the state of the registers can be maintained. There are three types of interrupts: external interrupt, which may come from input-output devices like a keyboard or a mouse, or a program trapped in an infinite loop can be exited, for example, by an external interrupt. Internal interrupts, on the other hand, is a second type, and can be caused by the invalid instructions, over and underflows of the ALU, or a divide by zero operation, or even a stack flow or overflow. The service programs used for internal interrupts take corrective action to address these issues. In contrast to the other two interrupts, software interrupts is the third type and can be triggered by executing instructions. These type of interrupts are usually used by expert programmers who can switch between user and system modes of the operation. Anyway, so today we've covered many more related trade-offs in the design of ISA, yet it's impossible to cover all the details as the modern ISA has many more fields in the code and operations which make them very, very comprehensive. We tried here to keep it general and applicable to all of them and for general audience. But the interested audience is referred to the links provided throughout the class. So I would recommend you guys take a look at those links to learn more about the details. And next, we will start writing assembly code for a given architecture. Hopefully, we will stick to few, toy ISAs in the beginning and to understand the fundamentals, then maybe write some more advanced codes, for example, for MIPS architecture, if time allows. So please feel free to shoot me emails if you have any questions about today's lecture, and I'll be more than happy to address them. And thank you very much, and see you soon.